My name is Milan Delor. I am an associate professor of chemistry at Columbia University in the city of New York, and I am a recipient of the 2022 Beckman Young Investigator Award. Arnold Beckman drew from his knowledge and interests in a broad array of fields, from chemistry to electronics to glassblowing, to develop some of the most useful analytical instruments ever developed, like the pH meter and the spectrophotometer. He pushed to develop highly reliable, quantitative instruments widely accessible worldwide. A defining feature to me is that these instruments have had a huge multiplicative impact on essentially all scientific disciplines. This legacy continues through the Arnold and Mabel Beckman Foundation, whose various programs continue to multiply this impact, including through the Beckman Young Investigator Program, or BYI. Through this award, my group was able to develop a range of powerful microscopes to directly image energy flow in space and time. And in the spirit of Arnold Beckman, we refined these microscopes into truly quantitative instruments that many other groups have started to implement in their own laboratories.
A big theme of research in my group is to find ways to move energy in materials in a way that is essentially lossless or with very minimal resistance. A very famous way of achieving this is superconductivity. But superconductivity requires typically very low temperatures or very high pressures. And we want to try to find an alternative to this that would allow us to move energy with minimal resistance at ambient conditions, so at room temperature and ambient pressures. And one way that we found to do this is to hybridize electronic particles with long wavelength excitations like acoustic waves or light that naturally sort of exist in the materials. And that has allowed us to find several classes of systems that really allow us to move electronic energy with essentially minimal losses at room temperature. These outlines here are the outlines of a two-dimensional material. And the width here is about 100 times smaller than the width of a human hair. And we're injecting electronic energy locally here using light. And then we are basically filming how that electronic energy moves at about 1 trillion frames per second. And in this particular material, propagation speed is really remarkable. They show electronic energy that flows with minimal resistance even at room temperature. The group essentially developed these microscopes that allow us to film this energy flow at very high temporal resolution as well as spatial resolution. So this is quite a unique way to look at the transport properties of a material that doesn't require building a whole device. We can optically look at the transport properties of both electronic energy as well as other types of energy like light and magnetic energy moving through these materials.